June Solstice Observations, Flat Earth and Globe Earth, Part 2, Azimuth of Sunrise and Sunset. So this video is borrowing some content from a previous equinox video, but I add a whole lot of more calculations, a lot of formulas, so just make sure you have your pencils sharpened. But truth be told, this really is a reworking of the December solstice observation of the same name, the Azimuth of Sunrise and Sunset. Now I do want to give you a disclaimer, a homegrown math disclaimer. Basically every single formula in this entire presentation was derived or actually just created by me. I literally sat down with a piece of paper and started sketching out drawings, and I was figuring this stuff out myself. And I did it using circles and spheres, and I actually duplicate my steps during the presentation, so you can actually see exactly where the formulas come from. So there isn't a single formula in this presentation that I got from anybody. It was all made up by me. And having said that, that means that it is not exactly correct, because since I'm using very idealized concepts, I'm using things like a geometric sunset, which I just made up. It doesn't exist. And it's where the center of the sun crosses the horizon. That's not really when sunset happens. In the real world, the sunset is when the top of the sun crosses the horizon. So therefore, the results you'll get using my calculations will be, maybe a degree off. But you should be able to make a good comparison, flat Earth versus globe Earth. Even though, my calculations aren't perfect. But I just want to give you a disclaimer. Alrighty, so this is part 2 of our 3 video series on the June solstice. So we've already measured the angle of elevation of the sun. Now in this one we're going to predict the azimuth of sunrise and sunset, and in the next video we'll look at the path of the sun. So preparation and tools. First we're going to do some exploration in Google Maps, kind of plan out where we want to make this observation. Then in Google Maps, we want to find, ideally, we want to find an east-west street. And if you can't find an east-west street, you can just find any other straight street that has nice curbs or sidelines that you can make a comparison to. You also want the time of the sunrise and the sunset. And then you just can use any camera, but you will, in the field, you'll need a yardstick and a protractor. So here's an example of, and this is actually Kimberton or Phoenixville near me. If you drag the little Street View guy onto the map, you'll see, actually this was in, I took the screenshot on Christmas, so the little Street View guy's wearing a Santa Claus hat. But you'll see all the streets glowing blue where they have taken pictures. And you're just looking for a straight street. And once you get there, if you click on those little arrows highlighted in green, the little curving arrows, that'll kind of align, north, south, east, west, and you get a kind of a good sense of what the conditions are in the real world. Now, next you want to look up sunrise and sunset times for the solstice. So for 2018, the solstice will be on June 21st. So this is using suncalc.org. You can also get the same information from time and date. Please notice that time and date usually gives you these numbers a month at a time, so you have to scroll down for the solstice date. Or you can actually use just a local authority, like a local website. So this is philly.com for Philadelphia. The trouble with that is that at least my weather page, it only shows today's sunrise and sunset. You can't you can't pick a date. So it doesn't really matter how you find this information. Make sure you get out to the field 10 minutes either before sunrise or before sunset, so you can get set up. Next, you're going to make a careful observation. So at the time of sunrise or sunset on the solstice, you want to find the azimuth of where the sun's peeking over the horizon. So that's the compass reading. All right, so this is pretty close. The sun's peeking over the horizon. Obviously, this isn't you're not in the city streets, but this is the sort of the moment we're looking for. This is a nice photo, but you cannot see the sun peeking over the horizon, so this is not this is not what we're looking for. And the sun peeking over a building doesn't count. We want the sun to be peeking over the horizon. So when you're out there in the field, and you just have to kind of figure this out on your own, you try to take a yardstick and sort of point it at the direction of sunrise, sunset. Maybe you have to get down on your hands and knees and kind of sight along with the yardstick, or if you have like a table or something. But you really want to point that stick towards the sunrise or sunset. One thing you can do is if you put the stick up on its side, or actually if you put a pin in one end of the stick, you can actually look at the shadow on the stick itself and try to have the shadow that the stick is casting be along the line of the stick. And then you're going to measure the angle that it makes with, say, the curb with a protractor. Now here's an example of an overhead view. There's a extremely large yardstick down there. So this is sort of an example of a downward photo. You want to be able to measure that angle. Now, what if you were not able to find an east-west street? So here's an example. There's a yardstick. It's on a curb, and it's pointing in the direction of sunrise, but it was actually taken on that township line road, which goes straight for a ways. So what you do is you take your photo, and then you can align the photo with the map, right? And if you align the photo with the map, then you can actually use your protractor, and you could figure out the azimuth. In this case, the azimuth is 72 degrees. All right, so it's a several-step process. Now, if you are really advanced and you want to get kind of technical, you can actually make a cardinal azimuth tool. And this is detailed in another video where I actually got out in the field and I measured this stuff on the equinox in September of 2017. So it really is made of 4 yardsticks that are pinned together in a very precise manner using a little bit of trig to match up with a landmark in the real world. And then you have this swiveling azimuth pointer. So you make the cardinal azimuth tool, but then you swivel the pointer around so that you could point to sunrise or sunset. And there's a picture of me out in the field actually using this tool, and it has a compass bearings diagram, so you can get a pretty precise reading. Now, being that you're going to be out there in the field, and it's really easy to confuse, north, south, east, and west, or at least like whether you're supposed to be adding or subtracting. So just pay attention to your math. Just double check your math. So 90 degrees is due east, 270 is due west. A lot of times you may be using a protractor that is built into a graphics program, and oftentimes these protractors have due east be 0 degrees. Because that's on the unit circle. 0 degrees is due east. So you just want to be careful you do your math right. So we're going to be comparing our expectations for a globe Earth versus a flat Earth. So just to remind you, on the June solstice, which is approximately June 20 or 21st each year, on the globe, the North Pole is tilted towards the sun, 23.4 degrees. Whereas on the flat Earth map, the sun is simply traveling a circuit above the Tropic of Cancer. So we're going to first do a flat Earth analysis. So it doesn't really matter the flat Earth you pick. So the only thing you need is the fact that the sun travels around the North Pole. So if your flat Earth map does not have that, then this analysis won't work. So if you need the North Pole, you need your location, and you need the path of the sun above the Tropic of Cancer. So if you have these things on your map, whatever map you choose, you'll be able to do these calculations. So on the John Abizaid map, notice that you can't actually see the continents. They've labeled where the continents are, but you could actually use this map because you can actually see where the tropics are. Now, as long as you can find your location on this map, then you can do the calculations. You could also use the Ferguson map. And you can use any other flat Earth map, as long as the North Pole, the sun goes around the North Pole. So I'm going to stick with the Gleason's map because it's the most popular. It's the AE, or azimuthal equidistant projection. And it'll make the calculations very, very easy. So we're going to figure out the azimuth of sunrise and sunset using a multi-step procedure. So first principles, a degree of latitude is not a measure of distance. It is a measure of distance. It's not a measure of an angle, because on the flat Earth, from the North Pole to the equator is not an angular change. It's merely traveling a distance. So we're going to call these land degrees because latitude is measured in degrees, but we're putting them across the land, so we'll call them land degrees. So therefore, from the North Pole to the ice wall is 180 land degrees. And we're going to figure out how many land degrees your location is from the North Pole. And then we're going to locate the proportion of the sun's circuit above the Tropic of Cancer that's providing sunshine to your location. So what this means is the sun does a circle in 24 hours. And if you can see, say, 60% of that circle, like you know what time your sunrise and sunset is, and just doing the math, you could figure out what portion of that circle is. And then you could place the sunrise and the sunset on that circle. And then you're going to analyze the triangle that is formed, the North Pole, sunrise, sun to your location. So let's take these one by one. Number one, first principles. A degree of latitude is a measure of distance, not angle. It's land degrees. So again, we have North Pole, which is 90 degrees north. We have the equator, and then we have the ice wall, which is 90 degrees south. So we're going to call these land degrees. And then we're going to say that it's 180 land degrees from the North Pole to the ice wall. All right, so we're going to eliminate the mention of latitude. We're just going to call these things land degrees. And then we're going to find out how many land degrees your location is from the North Pole. So if you have your latitude and you're in the northern hemisphere, it's simply 90 minus your latitude. Okay, 90 minus your latitude will give you your land degrees from the North Pole. And the southern hemisphere, land degrees D will be 90 plus your latitude. So for example, if you were in New York City, which is at 41 degrees latitude, you could do the math. And if you're in Sydney, which is 34 degrees south latitude, you can do the math as well. Number 4, we're going to locate the proportion of the sun's circuit above the Tropic of Cancer that's providing sunshine to your location. And then we're going to place endpoints for sunrise and sunset. So again, the sun travels a full circle above the Tropic of Cancer in 24 hours. All right. So in our example, Philadelphia, the sunrise is going to be at 5:32 in the morning on the day of the solstice. The sunset is going to set at 8:33 in the evening, which means that the length of the day is 15 hours and 1 minute, or 901 minutes. So in a full day, there's 1,440 minutes. All right, so 901 divided by 1440 is 63%. So the sun is going to travel a full circle in 24 hours, but 63% of that circle will be visible from Philadelphia. All right, hopefully that makes sense. So what we'll do is we'll reorient the map. The 63% of 360 is 225. So we're going to reorient the map, and we're going to locate an angle that is 225 degrees of sunshine. So again, this is Philadelphia, PA, and there is a 225 degree angle. The sun is visible that entire time. All right, that's for a Philadelphia observer. So then we're going to zoom into this, and we're going to analyze the triangle that's formed, the North Pole, the sunrise sun, and your location. So again, there's Philadelphia on the map. We've got the sunrise sun marked, and then we'll also take a look at the North Pole. All right, so we're going to form a triangle. All right, so this triangle, ultimately what we want to find is the azimuth of sunrise from Philadelphia. Okay, the number of degrees from the North Pole that the sun is rising. That's the azimuth. That's what we're going to find. But what information do we have? Well, we know that Philadelphia is at 40 degrees north latitude. That means we know that vertical segment is 50 land degrees. This triangle is going to be measured in land degrees, by the way. So that's 50 land degrees. We also know that the sun is above the Tropic of Cancer, and that's at 23.4 degrees north latitude. That's measured from the equator. So we want to figure out how many land degrees that is. So again, since that's in the northern hemisphere, we do 90 minus 23.4 to get the distance from the North Pole to the Tropic of Cancer, and that's 66.6 land degrees. I'm going to write 67. And what's next? We're dealing with 225 degrees of sunshine in one day. Well, this sort of represents half a day. All right, from the sunrise to, say, solar noon in Philadelphia. So we'll figure out the angle at the North Pole. The angle that is with the vertex at the North Pole will be half of 225, or 112.5. So theta is going to be 112.5. I'll write 113 degrees on my triangle. All right, so if you guys remember from geometry, if you know 3 facts about a triangle, as long as it's not the 3 angles, but if you know 3 facts, frequently you could figure out all the rest of the triangle. All right, in this case, we're going to use the law of cosines. We know 2 sides and the included angle. That's important. 2 sides and the included angle. So we're going to use the law of cosines to find the third side, and that works out to be 97.39. All right, so now we know 3 sides of the triangle and 1 of the angles. So we can use the law of sines to find that angle. Again, that's the azimuth angle there in pink. All right, and that turns out to be 39 degrees. All right, we'll call that phi. So ultimately, after all that math, we found that the azimuth is going to be at 39 degrees in Philadelphia on the June solstice. All right, so that's the flat Earth analysis, but we have to duplicate it for sunset. So everything is proportional before solar noon and after solar noon. So we're simply going to take 360 minus 39. The sunset azimuth will be 321 degrees. All right. Now, all that math might have been fairly complicated, so I've made a calculator that you are welcome to use. If you have a Google account or a Gmail account, you're welcome to use this Google Sheets. And I tried to make it very user-friendly, so you can input your latitude either in degrees, minutes, and seconds using the green and the blue, or if you know your decimal degrees, you can simply enter the latitude as a decimal degree. You also need to indicate northern or southern hemisphere. And then you have to input your sunrise and sunset times. And it's going to assume AM and PM, but if you use 24-hour time, like military time, like for example 8:33, you can enter in 20:33. All right, so you can use 24-hour time there. So it's very, very user friendly. I'm accepting a different variety of inputs, and then what you see below there are all the calculations, all those intermediate calculations, and you can go back through the video and follow along with those calculations. And so ultimately we found that the azimuth would be 39 degrees. And so what are our predicted azimuths of sunrise and sunset on the flat Earth? You see the sunrise and sunset directions there. Now we're going to do a globe Earth analysis, and the math is actually going to get worse. But so make sure you get your pencil sharpened. So locally, on the globe Earth, locally you can represent the neighborhood where you are, the field you're standing in, as a flat plane surrounded by a sphere. That's the celestial sphere, including the sun. So on the June solstice, the sun travels in a path that is parallel to the path that it traced on the equinox. All right, and it is actually 23.4 degrees higher and parallel to the equinox path. So what we're going to do is we're going to try to find the azimuth of sunrise. So there's that little orange arrow from our observer pointing to sunrise. So we'll take our protractor and we'll just lay it flat and we'll just make a reading. Okay, we'll make a reading there. So let's come up with a plan. How are we going to find the azimuth of sunrise on a globe Earth? Well, we're first going to analyze the 3D view of the path of the sun in the sky relative to the latitude. Now, we've already started that process with that little diagram. Then we're going to analyze a side view and use some trig to make some measurements. Then we're going to project those measurements onto a top view and finish up with some more trig to find the actual azimuth. And believe it or not, I figured all this stuff out on my own, so if you think it's wrong, just try to tell me where I'm wrong, because I literally just derived these calculations. So here is the 3D view. All right, we see our little observer. We see the sunrise on the June solstice. And now we're going to transition to a side view. But first, let's make a few notes. The red arrow that's pointing upwards is pointing towards the north celestial pole. And so that angle that's formed is our latitude. So if we go in the other direction towards the equinox solar noon sun, that's going to be the complement. That's 90 minus our latitude. Okay, so that's going to be very important. We're going to call this angle theta, 90 minus your latitude. We'll call that theta, and that's the angle of the sun on solar noon on the equinox. So again, here is the 3D view, and what we're going to do is we're going to transition to a side view. So here's the side view, and those are the sun paths. So we've got our location in the middle, north on the left, south on the right. And we're interested in that uppermost sun path. So we're going to be interested in that point right there, sunrise, sunset. That is the June solstice sun path. That's the thing we're going to be interested in. So the interesting thing here is that there are parallel sun paths. Again, the sun is not traveling in the sky. That is simply an illusion. In the globe Earth model, the globe Earth is turning on its axis, and so therefore the sun appears to move in the sky. Okay, so these are perfectly parallel sun paths for our dates in question. And so since we labeled that one theta, since these are parallel sun paths, we can label all three of these angles theta. And again, theta was 90 minus our latitude. Now the other thing that's interesting is that you can map out the June solstice and the December solstice as being 23.4 degrees northward or 23.4 degrees southward from the equinox. Okay, that on the solstice it's going to be 23.4 degrees up or down from the equinox. So that's theta plus 23.4 or theta minus 23.4. And then now we have these two parallel lines. If you remember from geometry, two parallel lines cut by a transversal. You're going to get, it's called alternate interior angles. So we have another 23.4 degree angle. And so then what we're going to do is we're going to form a little triangle in there. So we're going to try to figure out this distance from the center, meaning our location, to the side view of the sunrise. Okay, that's that blue bar marked X. That's going to be our side view distance, and that's going to be very important. So there's the green line again, which is 23.4 degrees, and we need to measure a distance here, and so I'm just going to arbitrarily select 1 to be the radius of the circle. And throughout geometry, if you pick 1 to be your radius, you can call it a unit circle, and the trig is much, much easier with a unit circle. So that was an arbitrary choice. We're interested in finding the value of X. So now that we know our theta, which is 90 minus the latitude, we can use the law of sines to figure out, at least solve for X, okay, to solve for X. So there's the law of sines. We solve for X. We get X to be the sine of 23.4 degrees over the sine of the quantity 90 minus our latitude. All right, and we're going to file that off to the side. We're going to use that in a few moments. So now we're going to transition to a top view. We're going to transition to a top view. So the thing we want to keep in mind is where the sun is rising on the June solstice. Okay, so we're going to pay attention to that yellow spot. That's the sunrise on the June solstice. And we're going to transition over to a top view. Okay, so there's that yellow spot. We're going to lay a compass rose down there, and we are trying to find the azimuth of that sunrise. All right, so let's draw another right triangle. And again, this is a unit circle, so the hypotenuse is 1. That top leg is X, because that's parallel to that orange bar labeled X. And the angle, we're going to make this angle, we're just going to call it D. And it's the angle of northward deflection. So we have due east is 90 degrees, but the sun is rising north of due east. So how much deflection north? We're going to call that angle D. All right. And now we're going to do a little bit of trig to solve for some of these things. So first off, the sine is opposite over hypotenuse, right? SOHCAHTOA. So that's x over 1 or just x. Sine of D is x. And so to solve for D, it's simply the inverse of the sine or arcsine of x. All right, so that's D, but now we're going to substitute in what we know x, that was that little formula off to the side. So now we substitute, and then we can actually solve. All right, so taking that little angle D, that's going to either be north of 90 degrees. In other words, we're going to take 90 and we're going to subtract D. That's going to give us our sunrise azimuth. To get the sunset azimuth, we can start off with due west, which is 270, and simply add D. So that will give us the azimuths of both sunrise and sunset. All right. Now, those calculations may be a little tedious. So again, I've got an Azimuth calculator. It's the same calculator. It does both globe Earth and flat Earth. So here is our the inputs. And again, this input is showing the latitude in degrees, minutes, and seconds. Again, you can use a decimal latitude if you like. This calculation does not need sunrise and sunset times. It is purely based on geometry. And then the sub-calculations, we've got that angle of northward deflection there. And finally, I'm sorry, here's the angle of northward deflection. And then finally, it's calculating the sunrise and sunset azimuths on the globe Earth. All right, and here's a comparison to the Gleason. Again, it's one calculator, and it does all the calculations. So this is pretty interesting. For Philadelphia, the calculations are 20 degrees apart. Now that should be noticeable. If you are out there in the field and you are making a very accurate field azimuth reading, again, precision is key, then you should notice a 20-degree difference. So hopefully your field results, you should be able to match them to the results from this calculator. All right, so let's summarize what we did with the flat Earth. You could pick your map or model and trace the path of the sun above the Tropic of Cancer. You can use the sunrise and sunset times to calculate the portion of this path in sunshine for your location. And then you could fix the location of the sunrise sun. And then you're going to measure the azimuth angle from your location to sunrise using that triangle. All right, and then subtract that from 360 to get the sunset azimuth. So that's how we did it on the flat Earth. On the globe Earth, first off, we remembered that the solstice path is a tilted circle dependent on your latitude, parallel to the tilted circle on the equinox. And this is 23.4 degrees northward and parallel to the path on the equinox. So we can use a little bit of trig to find out where the circle intersects the circle of your horizon. All right, and again, here's an overview of the entire calculator, and I do have a little bit of directions there, and there are a few assumptions. So for example, from the distance from the equator to the Tropic of Capricorn is 23.4 degrees. All right, so if you'd like to share your results, YouTube user Cara Diane has set up message boards. It's at flatearthmath.boards.net, and you can share your azimuth and your latitude, and compare with other people. All right, the next video in this series will be on the path of the sun using a shadow stick sundial. So here's a nice quote from Mother Teresa: "Spread love everywhere you go. Let no one ever come to you without leaving happier." Thank you.